a little different voice. And how's everybody doing? Good. Metal, and let's just get this straightened out. Here we go. Okay. Did everybody, I get that people have been keeping up with the videos by the look of it anyways, when I see people have watched, so that's good. So you guys know next week is intercession week or break week. So there's no classes next week. And on week 9, we're going to, get the test. And so what I plan to do is do a short video review for the test, but in the nutshell, for now, the test is going to encompass everything that we've covered up to and including chapter 9 as far as roofs goes. So really we're going to be looking at the zoning, the permit, not the zoning so much, but yeah, that's in that chapter that we started with, which was chapter 5, the site plan aspect, the foundations, floor framing, wall framing, and roof framing. So also, I'm probably going to have about a few questions that'll be on the Brook drawings. So I've started to give you get you oriented, looking at the drawings, which is tying the material that we've been discussing to how you actually build something and review it. I've got another video that I'm going to release probably after this class, which is, again, it's like the one that you watched last week, except it's going to be on details, understanding details and reviewing details and how to interpret details. I think that'll be particularly helpful too for your, your assignment that you're going to do where you're trying to figure out what's a detail of some part of the house. So I'm going to post that right after the class. So that should be helpful for that. There'll be another quiz this week, so that should be up probably in the next day or so. Again, it'll probably be similar to the one last week, which should be interpreting some information from the drawings. That should be getting you ready. But as I said, I'll do a short video that will sort of give you an idea of the content of the test. But they're going to be multiple choice, and so it's going to be following that kind of, you kind of get the flow of the multiple choice either from the book or from the quizzes we've been doing. So I think you got a good understanding of that. The test will be written at the same time as the class. So, instead of coming here, you just go online and you do the test during that particular time frame. So if the test is 9 to 11, then you can log on at 9, like you should have access to the test at 9 o'clock, and then you can work on it for that period. And you'll have so much time from when you start the quiz till when it, or the test till when it finishes, which will be probably about an hour and a half, hour and 40 minutes, something like that. Okay. So that'll cover that part of it. All right. So that's giving you a little bit of heads up. I'll probably give you a touch on that near the end again, just for people that came a little bit after. and they're probably still going to be coming in the next few minutes. So just to get into the lectures on roofs, I think is important to try to understand. Probably roofs is the, well, at least with the framing part, is the most complicated part of the house, to be sure, as far as the terminology and the layout and all those kind of things that come into play with it. So I'm just going to get this so I can see people. And there. No, you don't need to be in the live session, Anthony, for the test. You would just go in and do the test on your own. So you don't have to be in the live session to do the test. What I'll probably do is the first like 15 minutes or so, or 20 minutes of the test time, I will probably go in the live session and sit there in case somebody's panicked that they get stuck or something. So if you need to, you could probably jump into the live section for 5 minutes or 10 minutes. I'm not going to stay in there the whole time, but probably the first 10, 15 minutes. No, not able to backtrack for the test. Okay. So, and that's it. So the test should be following more or less the format, the way I've been doing it with the quizzes up till now. But you'll be limited on the time frame, but you've been limited on the quizzes too. You'll have to move at a bit quicker pace for the test, right? Because there's going to be probably somewhere between 35, 40 questions. So you have to move at a quicker pace. Okay. So yeah, so for roofs, I just wanted to recap some of the important things regarding the roofs. So there's a lot of terminology that you have to deal with roofs, and just getting used to it just takes a little bit of time. Projection is a horizontal measurement out from a wall. Overhang is sort of the sloping measurement. So that's the difference between the two. I would say, in all honesty, these two get mixed up all the time in the real world, what they call it. I think a lot of times when people say overhang, they mean projection. But that does come up fairly frequently. And big one is the span. If we're calculating a roof rafter, the span goes from the outside of the frame wall to the outside of the frame wall. Depending where your bird's mouth is cut to, it might be the outside of the sheathing to the outside of the sheathing. And that's an important measurement, because then the calculation, if you know what the span is and you know what the unit run and unit rise is, then you can calculate the rafter length. And to be honest, you can calculate like a hip roof, all the rafters for it, from the ground. If you know what the length of the building is, what the span of the building is, you can calculate the lengths of the rafters all from the ground and lay it out from the ground and just pass the rafters up, and they should fit. Sometimes the hip rafters might be a little bit off if the building's a little bit out of square, but other than that, it should all fit. So I did put a link for a video it's not a bad video. It's just pretty simple. So it's a little bit easier, I think, if you watch some of those videos, just to visualize what's being discussed, right? So if you're having trouble sort of understanding the concepts, I think a few of those videos can be, if it's the right video, because there's some pretty bad videos there too. But if it's the right video, I think it can give you a reasonable understanding of how a rafter is laid out and how it can be put into place. There's always some nuances and differences of how the terminology or how the layout is done, but at the end of the day, math is math. And so in this case, you take the span, you divide it by 2, and that gives you what we call the run. All right, often called the total run, because we run into problems. We get run, and then we get unit run, and they get mixed up a lot of times. Unit run is pretty much most of the time given as a measurement of 12, like 12 inches, right? And then your unit rise is given as a number, probably 5, 6, 7, 8, 9, and that's your unit rise. So it's pretty standard, those sizes. And your slope, that's the relationship between the unit rise and the unit run. And that slope that's here would be the same as this slope overall that's here, all right? It's just proportionally bigger, this is. So what we would do is, if, for example, if we knew what the span it was, so say the span is 20 feet, then that would make the run 10 feet. And so if the run is 10 feet, then, and we know that our unit rise, let's say is, let's say it's 512. All right, so it's 512. Okay, so if it's 512, then what we need, all we really need to know is this is going to be 10 steps. So this is going to be 10 steps because we said this is 20 feet and the run is half. So that's 10 feet. So it's going to be 10 units of run or 10 steps. And so for every 12 inches you go along, you're going to go up 10 inches. Sorry, you're going to go up 5 inches. You said 512. For every 12 inches you go along, you're going to go up 5 inches, right? Because this is a 512 roof. So the hypotenuse, we need to know the hypotenuse of 5 and 12, all right? And if we know the hypotenuse of 5 and 12, then that can be helpful for us. So in the case of 5 and 12, you use the Pythagorean theorem. And so it's going to be 5 squared plus 12 squared. That's going to give you 169. And 169 square root of that is 13. So your unit point length is going to be 13 inches. So we've got 10 steps. And every time we go 12, we go up 5. How long do we go this way? Anybody want to throw that in the chat? 13. Right. Right. That's right. So then, if we've got 13 inches, so we got 10 steps. So if we want to find out what's the theoretical length from here to the center, what would we do? I'm looking in the chat, see if who's got the number. Okay, Graham's got it. So 13 times 10, so we got 130 inches. That's it. So if you know that, that's going to be the point length, theoretical point length of the rafter. And the reason I keep saying theoretical point length or theoretical line length, they mean the same thing, is that that's to the middle, to the building line. We call this the building line. So then I have to deduct half the thickness of the rafter, the ridge. So the ridge is typically 1.5 inches. It's not always 1.5 inches, but it's typically 1.5 inches. If you have a ridge beam or something going across because you have a cathedral ceiling, then it would be wider. So it's always good with this kind of stuff to know what's the basis for the calculations, because then the thickness of materials, you're just adjusting things based on the material sizing. So all we would do is we would horizontally measure 3/4 of an inch, and then we would do our plumb line. That would be our cut line for the rafter. So the unit rise, if you hold your framing square at 5 and 12, then the 5 side is always going to end up plumb. The 12 side is always going to end up horizontal. So anytime I lay out something, if I'm marking on the unit rise side of a framing square, it's going to be plumb when the rafter goes up in the wall. So it would be actually plumb when it goes in the wall. In this case, I used a total run of 4 foot. So my span would have been 8 foot. And then it's the same idea. It would be 4 times 13, right? So same idea. Where people get a little bit bogged up with, where students get a little bit bogged up with is simple math, usually with this. When you're dealing with inches and imperial system, you're dealing with fractions. And so what you want to do is convert the fractions to decimals. This was a nice even number, so there wasn't any fractions involved. You know, it's 48 inches, it's 4 feet, nice even number. I could have given you a span of 21 foot, 6.5 inches, right? And then you're going to be getting into fractions. So that's kind of the difference that you would deal with that way. And of course, on the framing square, as I mentioned in the video, you look at basically along the edge of the framing square and you will see numbers. And then you will see sort of a table on the left and it says length of common rafters per foot of run. So the advantage that is, it's already got it broken down for you. You don't even have to do Pythagorean theorem. It's already there. So this would be for a 412 roof. This would be for a 512 roof. And then if the framing square kept going, I've got it cut off, it would have 612, 712, 812, and so on, right? So it does that for common rafters. It does that for hip and valley rafters. It does that for difference in lengths of jack rafters. All of those things. It just prescribes it for you. If you know the math, but that's behind it, you don't need to do any of that though, which kind of is my preference, to just know the math behind it so I don't have to remember those things or depend on those things. But today too, we have calculators that even do some of the extra calculations for you. Construction Master is probably the best known one, and it does calculations with fractions of an inch, and it has, you know, you enter in the span and you enter in the rise, and it gives you what the point length would be right away. Like there's things like that, right? But I think it's important to have some fundamental math just to have an idea or a sense of it. I don't think you guys are going to be framers, but it's a good idea just to know some of the basis behind it so that when there's a trade doing some work, you have some fundamental knowledge of how things are done. You know, those of you that may be interested to go further with it, you can look at a hip rafter. Is once you figure out the units of run, you're halfway there. The difference is a hip rafter, if it's for an equal slope roof where they slope the same on both sides. The only difference is the unit run is no longer 12. It's actually the hypotenuse of 12 and 12, because a hip rafter runs at a 45-degree angle in plan view. So it's the hypotenuse of 12 and 12, which is 16.97. So all you need to know is the units of run, which you already know when you did the common rafter. You need to know the slope, change out the 12, use 16.97. That will give you the unit point length, and you take your 4 and you divide it and you multiply it by that number, and that will give you the point length of the hip rafter. Done. It's a little bit more complicated with the deductions that go on, but that's the essence of it. So my point is, once you know a span and you know a slope, you can calculate pretty much anything you need to calculate with manual roofs. What happens too is over time, you know what, there's very few framers that are very good at laying out roofs. The ones that are good at laying out roofs are the ones that are always employed. That's usually the way that works, because what good is it keeping everybody if they don't know how to do it? So usually the person that is really good at those layouts, they're the ones that are, you know, there's a big recession or something, they're still working. And they're the most productive and smart as far as not wasting things, etc. So I've got let's see if maybe give you guys I was thinking maybe we try and see how you do on these. Why don't we try and see if you can take a few minutes and maybe for now, just do the first two. Just do the first two. Well, those are super fast. You can go ahead and do all 4, right? But we'll just do the first two for now, and we'll see what you come up with, right? And so we're calculating the total run. So divide the span by 2, right? Convert run to decimals. So make sure that whatever you've got in run is decimals, not inches, right? So it's got to be decimals, decimal feet. And then calculate the hypotenuse of the unit rise and unit run. And then multiply the units of run by the hypotenuse to arrive at the point length. So see how you do on those. Take a few minutes. And while you're doing, and actually, do you see it? Maybe you don't see it. Oh, okay, no, I didn't switch screens. My fault.
Yeah.
Yeah. My fault. Okay. So I'll do that. Stop share and share. I switched screens. This one. Okay, so I'll go through that again. So just do the first two. Try to figure out the point length of the common rafter. And this is just a reminder, calculate the total run. So divide the span by 2, convert run to decimals. It's got to be in decimals. So you're going to have a little bit of problems with the second one here. You got to think that one through a little bit. And think of run as units of run or steps, right? So think of run. So then you've got the steps. Calculate the hypotenuse of the unit rise and the unit run, the hypotenuse, and multiply the units of run by the hypotenuse to arrive at the point length of the common rafter. Just do the first two. If you're super fast, you can jump ahead and just go through it. I was going to, what was I going to do? I was going to look for the answers, but I could do it separate. 412. Maybe. I'm just going to write it out. .65. Okay. And 512. This guy A keeps coming and going. And if you figured out your answer for the first two, get it so that it's in feet and inches instead of just inches. Okay. Okay, how are we doing? We good? Chat. Okay, I'm gonna I'm going to put up the answer to the first one, right? So I'll put up the answer to the first one. Screen share. And let's see. So where is it? PowerPoint. There we go. Okay, everybody see that? All right. So what I did was you have 20 foot for your span. So you divide that in half, that gives you 10 foot. You get the hypotenuse of 4 and 12, 12.65, right? Then you know that there's 10 units of run or 10 steps. So that's 126.5 inches. And if you want to put that into feet, right? If you divide by 12, it goes 10 times. You're going to have 6.5 left over, which is 6.5 inches, right? So you've got 10 foot, 6.5 inches. That would be the point length for your, that would be the point length for your common rafter. All right, so the next one, which is a little bit more tricky, is 31 foot 6 inches wide. So I think people that are not used to feet and inches have a lot of trouble with this kind of thing. So the way I usually break it down is you can do it different ways. And if you're getting the right answer, just do it the way you want. But if you have a lot of trouble with feet and inches, then what I usually do is I just take the total feet and deal with that first. I divide it by 2. That gives me 15 foot 6 inches, right? So half of 31 is 15 foot 6 inches. And then I take the 6 inches, I divide that by 2. That gives me 3 inches. So then I just add them together, which is 15 foot 9 inches. So what you have to do is get this 9 inches into decimals, decimal feet. So there's 12 inches in a foot. So 9 divided by 12 gives you 0.75 feet. So this is the same as that, 15.75 feet or 15.75 units of run or steps. So we have those steps. And then we, again, have the hypotenuse. So the hypotenuse, that's no problem. I'm sure for you guys, you just have to figure out the hypotenuse of whatever it is. We'd already done one with 5. So that gives us 13. 5.75 times 13 equals 204.75. And then if I want to find out, well, I could just divide this part, the 204, the whole number, by 12. And in this case, it happens to go exactly to 17. So that's 17 feet. And what's left is 3/4 of an inch. So 17 feet, 3/4 of an inch. And so that would be the point length for this rather large roof that way. So that's really how you calculate it step by step. Does that make sense? So I'll probably throw 2 or 3 of those questions into the quiz just so that you get it down, work on it, and see it that way. Maybe you want to take a picture of this one or what have you, or then you have it, the step by step. I'm used to doing this live on a whiteboard, and I just do it all the time. I never really had it in slides. I always just do it from the top of my head that way. The 3 inches is half of 6 inches. So the 3 inches is half of this 6 inches. Like you can do it other ways, but you just got to remember this is not a decimal. That's where people get tripped up. So a lot of students, they'll just go 31.6 or they'll go 31, you know, they'll do different things, right? You could have went 31.5 and that would have worked, right? If you know that 6 is 6/12 and that's half, then you could have done it that way as well. But I usually find just looking at it sort of logically, this is 15'6", that's half of this. This is half of that. I put them together. I just find that some students that grew up with metric, they have trouble with this with imperial because it doesn't necessarily make sense. All right. So this 15'9" is half of that. So if you add this or you multiply this by 2 and you don't get that, then something's wrong. That's another way of looking at it, right? Because it gets even worse, right? 31'6". I could have had, you know, 31'6" and, you know, 7/8 or something. It's a little bit more, right?
Sorry to interrupt, Tom. When you divided the 31 by 15, what happened to the 1?
The 1 is the 6 inches. So half of 1 foot is 6 inches.
But isn't it also 6 inches too? So it'd be like a foot 6 inches you'd be dividing by?
Well, you could do, you know what? Like you could say this is 30 foot and you got 1 foot 6 left. That would be 9 inches. So that would be 15'9" as well.
Okay.
As long as you're getting 15'9", there's a lot of ways to get there, right?
Oh, true. Okay.
So I'm just trying, as long as you're getting 15'9", not 15.9. That's the other, I keep saying that's where you get tripped up, right? 15'9" is not 15.9. And you guys, you know, if you're metric oriented, everything's decimal. And I'll be honest, imperial system, if you're trying to look at it like it's logical, it's not that logical. It's not as easy as decimals, right? So yeah, I'm just a good double check for you if imperial's not your thing. Once you've got it divided up, make sure that when you multiply it by 2, it works out to 31 foot 6 inches. So multiply that by 2, it's going to work out because you're going to have 30 foot and then you're going to have 18 inches. 18 inches is 1 foot 6 inches. That's where it's not as easy when it's the same thing with concrete volumes. It's why commercial drawings are pretty much all metric. It is so easy to calculate concrete volumes when it's metric, right? Your drawings are in millimeters and you have to come up with cubic meters. So as an example, if you had like I'll show you the picture. I think I can just show it to you. If you had a concrete slab that was 5,000 by 4,000 by 175. So if you had a concrete slab that was 5,000 by 4,000 by 175, something that looked like that, right? So if you had that, it's pretty easy to calculate the volume in cubic meters. Very easy to calculate the volume in cubic meters. You just got to first move everything to decimals. And to move everything to decimal, to meters from millimeters is easy. You just move it 3 places. So 4,000 becomes 4, 5,000 becomes 5, and 175 becomes 0.175. So you just move it 3 places. So your calculation for cubic meters would be 5 times 4 times 0.175. So if you want to know how many cubic meters of concrete that is, that would be 20 times 0.175. Which if I was really on the ball today, I could do it in my head. 20 times 0.175. I would just multiply those three together and I would get that, right? So I would have 3.5 cubic meters. So easy, right? So easy. But if I were to tell you that that this was 20 foot 6 inches by 14 foot 4 inches by 7 inches thick, if I were to tell you something like that, and I said I wanted it in cubic yards, I'd have a lot more work to do. I would have a lot more work to do, right? Because I would have to work it out to cubic feet, right? And then I would have to figure out how many cubic feet in a cubic meter and so on and so forth, right? So really there's 27, but I would have to work it out to figure out the cubic yards. So there's a lot more math involved in that process. So it's one of the reasons, there's a lot of reasons, but there's one of the reasons it makes it very easy to calculate cubic measurements when you're dealing with metric than dealing with imperial. And the same thing goes with even roof calculations and things like that. But roofs, you know what? It's pretty much always in imperial. So it's just easier to do in imperial. So you just deal with that part of it. You'll learn in your estimating classes how to do the calculations in imperial for concrete, but it's just, it takes a lot more effort on something that shouldn't. And that's where it would be worthwhile to have it like a construction master calculator rather than doing all the laborious stuff. Or to have a software program that would do it for you if you're doing estimating. Okay, so any questions on that? You guys are okay with that process, calculating a common rafter? Looks like it's okay. All right, so I'm just gonna switch and I'm gonna go to back to the roof. 3 and 4, did you do 3 and 4, Arslan? Maybe at the end I'll throw up the answers. So I only ask people to do 1 and 2. The other 3 and 4 you could try on your own, and why don't I, maybe at the end of the lecture I'll put it up because I do have the answers, so I'll put it up then. How's that, Arslan? Okay, so lecture 5, roofs, share. Yeah, so there's a lot of things to consider. Now, I think I was pretty clear in the lectures that the reason that we don't do conventional roofs or cut roofs as much is, number one, our buildings they're not small bungalows anymore. Like our houses are a lot bigger than they used to be. Very difficult to span long distances with rafters. Very difficult to get material that's that long. So like this example that I gave you with number 2, what's it, 17 foot 3/4 of an inch? Good luck getting 17 foot rafters, right? 16 foot is about the easiest to get. So there's limitations with cut roofs. The other thing is it takes more skill. The other thing is it requires larger lumber to span those distances. So the cost is much more expensive than it would be if you used roof trusses. So the advantage of roof trusses is you don't have to have the same kind of expertise that you have with cut roofs, but to be honest, we mix both of them together. We tend to mix both of them together. I think the Brook drawings, most of the roof is trusses, even the smaller sections of roof in the book, but the Doncaster and the Whittington drawings, Whittington houses, which is a very typical example. The main roof is roof trusses, and then the smaller roofs are not. So maybe I'll just, while we're there, open up maybe just the Doncaster drawings. So you can take a look at that. Look at a different set. We've been looking at the brook all the time. So maybe Doncaster. So the Doncaster drawing, you remember, you know by the title block which book you're looking at. Sorry, which drawings you're looking at. And if we go down to the actual roof, we can see in the actual roof that, let's get this up and this here. Okay, we can see in the actual floor plan the roof, and it says approved raised heel roof trusses at 600 on center. Approved raised heel roof trusses at 600 on center. And in your book, in chapter 9, towards the end, you see some examples of the various roof trusses from the truss drawings that are provided with the Doncaster house. But you'd also notice on that roof truss shop drawing that it's got like some angled lines that says conventional. And the conventional parts are things like this. See here? It says 38 by 89 spruce, number 2. Well, that means you're going to use 2x4 rafters, all right, at 400 on center. So you're going to place them at 16 inches on center with 38 by 89, 2x4 collar ties at mid-span. And a collar tie goes at mid-span, and it really strengthens the roof. So then you don't need to use as heavy rafters. So it saves on lumber. 2x4s are a lot less expensive than 2x8s, right? And 2x8s are more, a 2x8 is more than double a 2x4 because it's harder to get wider lumber. It's more expensive. Takes longer for the trees to grow, if you want to look at it that way. So you've got the collar ties, and then the ridge board is always going to be one size bigger. That's a building code requirement. So if your rafters are 2x4, your ridge board is going to be 2x6. If your rafters are 2x6, your ridge board is going to be 2x8, and so on. You know, if your rafters are 2x8, your ridge board is going to be 2x10. Same thing goes with hip rafters. If you've got 2x4 hip rafters, 2x4 common rafters, your hip rafters would be one size bigger. They'd be 2x6s. And that's because of the angle. When you cut the rafter at an angle, you want it to rest as much against the ridge board as possible. So that means this section here is actually cut on site. The main roof, though, you can see where it says girder truss and girder truss. The main roof is a truss roof. So the nice thing about a truss roof in this example is that you've got from one wall to the other wall, you can clear span. Like none of these interior walls are load bearing. So you can put those walls wherever you want. If you're an architect, you can design the layout without having to worry about picking up the loads of the ceiling joists, right? Because usually you have to worry about where the ceiling joists are going to lap over, and the ceiling joists are load bearing because they're carrying the weight of the ceiling. So that gives you a lot of flexibility with where you put your walls. And so that is very, very helpful in the design of the actual second floor. And it's very quick to erect. But things like this, they're cut on site. And then that is actually this, right? So that's that back of the house on the elevation. And that's built on site on top of the truss roof. Other roofs in this particular set of drawings that are cut roofs are the roof over the porch and the roof over the living room. I know because it says rafters, right? It's not saying trusses, it's saying rafters. So I know you're cutting those on site. It says rafters over here. That little roof that goes over the garage is also going to be cut on site. And these are the sizes of the actual rafters that are being used. So you can sort of see how that is working. You could see too when it says, we don't usually call it hip joist. I don't know why they call it hip joist, but it's usually called hip rafters, right? The the size of the hip rafters, like I said, they're going to be one size bigger than the common rafters that are used for that. So these will be cut on site. This little box window, there's the rafter sizes for it, right? So you got to look for the rafter sizes. You know, when you're reading construction drawings, very often the information's like right in front of you. You ever go to looking for your keys and you're looking everywhere for your keys and then you see it's like right in front of you. How could I not see it, right? Reading drawings is very much the same way. Tell you you're looking for something, and it's right in front of you. So sometimes you have to do a double take, or you just have to look away for a little bit and come back to it. The other thing I would also say with construction drawings, people get myopically focused, like they'll just focus in on here. He said, what's the size of the wall here, right? And they just keep looking here. Well, you got to expand your circle and look outward, and then you start to see, oh, 230, that goes to there. Oh, 230, that goes to there. Okay, so the wall is 230. Okay, so that tells me how much the wall is. How much is it from the edge of the outside wall to where the garage door starts? Oh, it's 300 from there. What's the opening for the garage door? Oh, it's 2520. What's that center portion? And then you can start working it backwards, right? So you start small and then you increase yourself and start looking further around outward. If you just get stuck on the one spot, then you're never going to find it. So it's trying to get that aspect. Now I'm looking at this stuff. I don't necessarily understand exactly what's going on. I really don't necessarily understand what's going on looking at this until I go down and, well, I could understand better by looking at the front. And with this particular drawing, very difficult to me. If I look at this, it looks like this is almost just going straight across, but you do see a little bit of difference in the height there, like from this, where the ridge is going against the frame wall before the brick here. So you do see that's a little bit higher and then it drops a little bit. But I don't really know by looking at just the front view. And so from a constructability point of view, you have to be able to look at things from different angles and visualize it three-dimensionally. So I would look at this, and then I would want to look at perhaps the right elevation. And then I notice, whoa, what's going on here? This is sticking out a lot more than this. So this part here is sticking out a lot more than that. So I'm noticing that. And then I look at the other side view and I'm like, whoa, what's going on here? This is really sticking out, right? This is coming out pretty far. So this actually comes out really far, right? So this really comes out far from that perspective. So you got to not trust just one view. You got to look at multiple views and start to synthesize that information in your mind and then better visualize it. Now, we may have a 3D model in some projects, and probably, in the next 5 years, probably in all projects. But for now, we still very often have the orthographic drawings. And we're always going to have these orthographic drawings. The difference is that we'll also have a 3D model. It's hard to get all this, the measurements and things floating around in a 3D model. Whereas this, you get the measurements and everything on it. But it is nice to have a 3D model that you can look at and you can rotate and you can see from different perspectives to get the visual view. So, but very often you don't have that luxury. So we look at that, we see that, I see that this is a gable end here. And then when I look at the drawings, it tells me I'm using 2x4s. When it said a hip, it was talking about this piece here. So these are hips, right? They're on the outside corners. This is, of course, all going to be a truss roof up here, except for on the back. This part here sits on top of the truss roof. It's built on top of the truss roof. Now, there is also a roof plan. So the roof plan is helpful too. For me, I can visualize what's going on generally pretty well. But if you watch the brick drawings, the video I did for the brick drawings, when I was looking at the gables on the one, I got tripped up a little bit because I hadn't looked at them, I think, since I really wrote the book, the 4th edition on the book. So I was looking at it and I was trying to remember if there was an issue with one of the ridges not shown. Because on this one, I remember on the original one, this hip was not shown. So on the roof plan, it wasn't shown. It was self-evident though, when you look at this and you look at the front view, that there has to be a hip there, right? So it was self-evident, but these things happen where a line might get missed. So you've got to try and pick up. Also, don't trust just one drawing. You've got to pick up from these drawings. Does everything seem in sync? Does everything make sense? And if you're only looking at this, then you would think this is like a shed roof, because if it doesn't show a hip here, then I would be thinking this part here just goes straight across and it's a shed roof. Until I would look here and see, oh, wait a minute, no, that's not a shed roof because it's not got a fascia down the side. It would be shingled. It's definitely not a shed roof when I look at it from the front view. There's no way that's a shed roof. So you have to look these things over and find them. I kind of actually debated on whether I should add that line, because sometimes it's good to have the drawings with mistakes in it, because that's the real world. To be honest, in the past, I've had students, why you give us this drawing? It's got a mistake in it. It's like, you should see what's out there. You should see what's out there, right? You get mistakes in the drawings. Where you have value is if you can pick up on the mistakes. If you pick up on the mistakes at this stage, it's not a big deal. RFI to the designer. No, I got to have a hip here. Fine, then you know. If you've got it half built, what are you doing? Why you got it like that? Well, and then there's this argument that takes place, right? And then there's claims, and then there's trying to settle these things. So you have a lot of value when you can look at a set of drawings and visualize step by step how it's going to be constructed. And even if you can't, by asking this particular subtrade the right questions to make sure they're clear, you're clear, the consultant's clear. That's really important when we talk about construction of any type, right? We're talking residential now, but any type of construction. And so, yeah, and as I've mentioned, it does take time to get used to looking at the drawings and visualizing what the components really are. While I've got these up, this is really interesting because this ties to the chapter on exterior finishes too. You've got a number of sort of details with the brick here. This is a soldier course. So when the bricks are standing up, it's a soldier course. The bricks going down the sides of the window, those are header bricks and they're stack bonded. So as I mentioned in that video, stack bonding is very weak. Like it would crack and you'd be able to push those if it didn't have metal ties, brick ties that would tie across between the brick and the header stack bonded. And you know what header stack bond, it calls it that. I think it says it on either the front elevation or the rear elevation or both. There it is, brick header stack bond. And then it's got W/10. So that means with 10 millimeter projection. So the brick that are header bricks stick out 10 millimeters. So it gives like a shadow line. It looks really nice. Like it just is a detail, right? You're not doing this for any other reason than to try to make it look interesting, to try to bring some attention to it. So it's an architectural aesthetic appeal to it. Same with soldiers. The only reason you're doing soldiers, it makes it more decorative. Sometimes they have soldiers on the top. Sometimes they have a band around the bottom. I think the Brook drawings has a band around the drawing. You know, you look for these different things. And of course, we've talked about lintels in 7, 8, and 9, chapters 7, 8, and 9. And of course, the lintels are the steel. And I've got that. If you're having trouble visualizing the steel lintels, make sure you look at the videos for chapter 10. Which is the exterior finishes, because I got a picture of steel lintels laying in a pile, and then I've got some good illustrations, and they're in the book too as well. So you'll see that as well. And remember, you get the lintels from the lintel sizes from these labels. And we go from the labels, we go to the construction notes. And the construction notes gives us all that information under the lintel and beam schedule. So 1 to 6 is wood, 7 to 12 is the steel lintels. We use the hexagon, if you've forgotten, to reference points. So if we see a hexagon on the drawings, we can look at, oh, what's number 17? I wonder what that's referring to. And then it says both sides of the steel beam, you're going to put a 1x4 to hold it in place, nailed up to the underside of the joist. So that's what that is referring to in this case. So all these little hexagons mean something. So you look for those bits of information that you can find on the drawings. And don't forget about the cutting plane lines. It cuts through something, it means you're looking in the direction of the point, and then you look for the reference. In commercial work, it gets much more better referenced. So the cutting plane line, instead of just saying A, B, C, D, like how many details are we going to have in a residential house? You could have a complex residential house and maybe you have 10 or 12 details, fine. But on a condominium building, you could have easily 200 details, right? And so to reference them, what they would do is they would say the page number. So they might say A23, and it might have 10. So on page A23, architectural drawings, page 23, it's detail number 10 on that sheet. So it would reference it and give you much more detail. I talk about that in chapter 16. We don't really get into it in this course, but I'm sure Nakshab's getting into that. So, but we want to be able to look at things, reference it, be able to orient ourselves. And then that's where it ties to everything we've been talking about. You have to know what you're looking at, right? So you have to know what a stud wall is and how it's framed and what the lintel is and that it rests on jack studs. And you have to know that solid bearing is that you're going to make sure that this is secured underneath. So the loads are transferred from the beam down through the wall to the foundation wall. So all of those kinds of bits of information you get through reviewing the drawings and trying to visualize what the components and the materials and the methods that you're going to use to construct the building are. So kind of gives you that flavor on that. So that's giving you an idea on the trusses on this. You see where it says here, Kent. So 245 by 235 LVL, laminated veneer lumber, right? And it's going to be cantilevered. So this part here is going to go back in this section here. So it's going to cantilever back in the wall so that it helps to carry the load of the garage, right? And I think it, where is it? Where it shows, yeah, look at that. There we are. The detail for this bracket, right, to also be placed on here. But a great deal of the strength is going to be coming from the cantilevered LVL that's going to go back inside this wall. Remember, cantilevering just means it's resting back and it's extending outward. So this drawing has actually a lot of cantilevers. If you remember from chapter 8, when we looked at the floor joist system, and chapter 7 and 8 both talk about the cantilevering of the floor and what that looks like. So there's a lot of images. There's a 3D image for you there if you're not absolutely clear on it, but you can get the sense for that. Other things, of course, we got a section detail for the whole house. And in the section detail for the whole house, gives you a lot of information. I'd always give a quick scan, like here, I can see, okay, so the laundry room is sunken. That's really confirming a lot of things. When I look at the drawings, it says down 2 risers or up 2 risers. So that's 380 millimeters. So we can see that in there. We can see the footings that are underneath the columns and the where the columns are. So that's why those are shown that way. And that's why they're thicker too, because they're column footing. They're typically a lot thicker than the strip footing that you're going to see at the side or around the house. Are there any questions that you guys have about trying to look at a set of drawings and trying to look at it from a constructability point of view? Any specific questions? No? Okay. Well, if you come up with one, type it in. I'm going to just go stop share. And that. Yeah, so I'll just go on to the bit on the trusses. So you guys see the PowerPoint on the roof rafter here? Good, okay. So just remember too, this image, ceiling joist, collar ties not shown. This is just showing all the components. There would be a ceiling joist going across here, and the ceiling joist ties the rafters. If you don't put a ceiling joist, the walls are going to bend outward in the middle. So the ceiling joist would hold the ceiling, and it also holds the walls in place. A collar tie, which we saw on the Doncaster drawings, goes about mid-span, and that makes the roof even that much stronger, and it means that you typically can get away with a smaller rafter in the design. This is all the names of the, this is all the names that you'll hear used. So the bird's mouth is the cutout of the common rafter, so it can sit on the plate. And just like our floor joist, it needs to have 1.5 inches of bearing that it sits from building code. You can't notch things like this because that would not work, right? So it has to be notched in a way like that. That would totally weaken the actual rafter. And when I say 1.5 inches, I mean on the plate, not counting, you know, that it's sitting on the plywood edge. Okay, so the truss roofs, a lot of different designs for roof trusses, endless sets of designs. You can do pretty much any kind of roof truss that you want, design-wise. They could have designed, you know, that cut roof on the back, that gable roof. They could have designed that with trusses if they wanted to, right? Sometimes they make a decision, oh, it's only 2x4s. We could frame this up probably just as quick as with the trusses. They might get damaged. Sometimes they'll just do the smaller stuff with a cut roof and the bigger stuff with the trusses. Other times they'll do the whole roof, everything with the trusses. I got to take another look at the Brook drawings. I can't remember if there's some parts that are cut. Probably there's some parts that are cut, but much more of it is, as I recall, is done with the trusses. Trusses are very vulnerable during construction. All right, so they're very vulnerable during construction. So we got to make sure that the roof trusses are braced, because they really are reliant on the sheathing. It's part of the design. Till that sheathing is on, it is very dicey. You'll find that a gable framed roof tends to be a lot more stable during the framing process than a truss roof. So you have to make sure that it's braced well during the construction. If the winds pick up or something like that, it could be a catastrophe where it becomes like dominoes and it breaks into 1,000,000 pieces. There's also permanent bracing that gets put into place. Those are indicated on the drawings. Usually you can see it on the elevation shop drawings where they're to be placed. There's that. Girder truss, just to be clear, is a truss that carries other trusses. So these are jack trusses. Just like you have jack studs in a hip roof, these are jack trusses, and they run into the girder truss. So the girder truss is carrying more than just its weight. It's carrying the weight of all of these trusses. So that's why it has to have solid bearing that carries down through the house that you see on the drawings where it says SB, where the girder trusses are, and it follows it down from one floor to the next floor. So a good example of it going up in construction. And then usually what they do is they just frame the hip, the little hip, extended hip, and jacks that are left in place. So it looks something like that. Sometimes they'll even come with the hips cut and the jacks cut. So it depends what you order. And of course, the gusset plates, that holds everything together so that things don't come apart, but they are very vulnerable during construction. So take care. And if you see them pop and somebody just slaps them back together, it's not going to have the same kind of structural strength. So there's actually a fix that you have to get an engineer to do, and it'll require pieces being scabbed onto the side and then certain sizes of nails and a certain amount of nails. On larger production sites, they usually have standard fixes, and then they just use that fix for whatever the problem is when it's a broken gusset plate. But it's supposed to be designed, not just whack it back together and it's good enough. Everything is fine when you whack it back together and it's good enough till 5 years later, there's a big snowstorm and the roof collapses and somebody gets hurt and there's an investigation, then all this stuff comes out, right? Lawsuits and everything else. And I think I mentioned this pretty clearly, but whatever hangers that you're using have to be the ones that are designed for the trusses. Because you could imagine it could be carrying a lot of weight at that one point. So you're not supposed to use just one that's from Home Depot. It's supposed to be designed and engineered to make sure that the gauge of the hanger is able to support that particular weight. So on that end, this stuff is very much what we talked about with the engineered floors, right? When we said engineered floors, you have to use the nails and the hangers that are supplied by the company. Because then if you're using some other hangers, then it's like, well, they're off the hook because you're not assembling it the way they told you to assemble it. So those are all things that come in. There's the solid bearing underneath it. I remember we had this house that we did, and it had the window over where the girder truss was. And so it said solid bearing right the way down. And so underneath the window, the rough sill, the inspector wanted us to put a piece underneath that lined up with the girder truss. And I wanted to say, I didn't say, I wanted to say, that's going to do nothing, right? Like the support that goes all the way down should be on the jack studs, because the jack studs are carrying extra weight because they're carrying it to the lintel, to the sides, and they should have the support all the way down, which they did. But no, this guy wanted it underneath that lined up with that. And I was like, well, in my head. But sometimes when you have an inspector and they're wanting you to do something and it's going to take 5 minutes to do it, better not to argue, just do it. Right? So sometimes you have to make certain calls with things. It was funny because he didn't seem to care about the jacks, that the support was going down. He just cared that it was there. So, and sometimes you get that with building inspectors. Sometimes the building inspector, especially in Toronto, they carry multiple things. So you might have a building inspector that also is the plumbing inspector. And so he or she might have been a plumber. And if they were a plumber, structural framing is probably not their thing. On the other hand, they might have been a framer and they're doing plumbing inspections, then they're probably not so good on some of those things, right? Because as I said, every area of construction, at least in our other course, we've been talking about it, is very specialized. And so this is just giving you the idea of the framing members, and then you can sort of see this is for that Doncaster house. So then that would be framed on top. These are your collar ties that it mentions that's going back and forth. So those are the collar ties that are going into place. These are the dummy dormers that just are there for looks, no other real purpose. So they're there for aesthetics. So they're not really serving any other purpose than that. Also, these H clips. So if you're running a project, make sure the clips go in between, because this is not tongue and groove, the sheathing. Your subfloor is tongue and groove. Roof sheathing is not tongue and groove, so that will sag if you don't have a clip in the middle. Roof trusses are typically 2 foot on center, and building code allows for very, very thin plywood for roofing materials. And if you're using the minimum of the building code, it's pretty bad in my mind. You should have 1/2 inch sheathing for your roofs, not 3/8. But this is 3/8, and this has got the H clip because it over time it waves, right? So it sags a little bit. Certain lights and some of the newer houses, you can sort of see the little bits of wave. Now it's not going to collapse. It's just, I don't know, just doesn't seem that that good for the difference that you see between 3/8 and 1/2 inch plywood. Like, you're not talking a lot of money, right? But every dollar counts when you're building thousands of houses. So going back, minimum building code, minimum acceptable standard, right? Review the truss drawings. So the truss drawings have numbers, and they basically situate themselves by the numbers. And so each number has a elevation. And so there in the truss drawings, each one of those numbers has a drawing like this with all the calculations below it and the engineer's stamp on it. And it's been designed for the snow loads in this particular area, going back to one of our previous lectures where we talked about the composite snow loads. So it's for that particular town or city based on its composite snow loads. And so that little rectangular boxes there, that's your bracing. So that's your bracing that goes in there. And then the different trusses, the bracing goes in, and that's to stop these members when they get under either under compression, potentially buckling. So that makes them more rigid. You'll notice that once the trusses get smaller, they don't need bracing because the pieces are so short, they're not going to buckle. So you'll notice that on the drawings in the textbook. And yeah, as I mentioned, so you've got this, you've got the jack trusses that are shown, the cuts that are shown. So in this case, it's actually showing the jack trusses that they would come supplied with it. All right, and they've already got the angle cuts that would go into place. And then this is the full jack truss, right? That would be going across to the girder truss. So these ones and these shorter ones are basically those that go across here and those that go across there. You see how he's got the angle sort of thrown in? That's saying, and I think if you look at the truss drawing in the textbook, it'll say conven, C-O-N-V. That means this you would frame in place. The lower roof, these little jacks that would go here. So they likely didn't supply these with the actual truss. Everything else though would be framed. It doesn't even show the gable roof right back here. That's because you're going to frame it later on top. And then you can have all sorts of brackets that may be required. You don't really see that. Toronto, we're actually in a pretty good climate. We don't get big hurricanes. I think if we ever do, we're going to have a problem. Certainly in areas like Nova Scotia, Newfoundland, parts of BC, you get very, very high windstorms. And so there'll be special brackets that are required. There's ones like this that attach to the plate. There's other ones that actually twist around and attach to the studs. So you pretty much have to rip the whole walls out, like windwise, because there is very often a negative pressure that's put on a house where the roof can actually blow off the house if there's enough winds being applied to it. So in some cases that may be a requirement, or in some cases somebody just wants to do extra than they above and beyond the building code. There are all kinds of ties for that. And then I spend a little bit of time at the end of that lecture and I talk about framing key points. And so when we wrap that up, a big part of managing this residential construction process is making sure that all the walls are where they're supposed to be. So you would take the drawings and I would never trust the framer that they put the walls in the right spot. I would never trust that. And I would be checking it as they go, because if you pick up on something, it's much easier to fix it sooner rather than later. So from a framing inspection point of view, you want to be doing the management by wandering around, making sure that you've got your eye on what's going on, or in lean construction, we call it a Gemba walk. It's a quality walk to make sure that things are going the way they should be going and you're observant to everything. We talked about lumber, how it shrinks, how it warps, how it twists, how it cups, how it crowns. You'd want to go with a straight edge. Check the walls at the midpoint. If there's a big buckle in it, you would identify the stud that's sticking out. You would do a saw cut through it. You would push it. You would put another piece beside it to straighten it to get that bow out of the wall. Very easy to fix now. A good carpenter can go around and fix all these defects with a straight edge if you've identified them in probably about an hour and a half, right? It's not days and days of work. Somebody that knows how to fix that can do it pretty quickly. But to leave it, now you've got this big bulge. You have trouble with the kitchen cabinets going on that wall because it's not straight. You have issues with your doors, perhaps. Maybe also the other thing you want to check, and I don't think I discussed this in the video, is, and it's something I think that it's worth noting for you, for sure. I probably discussed it in somewhere in the book. I doubt I would have missed that, but every time I read it, I start thinking I got to add something else. So if you go to like a floor plan, I always look at things like, actually, is it sharing now, the floor plan? Okay. So I always look at things like the doorway, and I would look at how they framed this. And I would want to make sure that whatever casing we're going to use on this project, it is not going to have to get cut. I'm going to make sure that, because you don't know, you could put 2 2x4s here, right? Under this doorway. This is a non-load bearing wall, so it's not going to support anything. So you could have 2 2x4s here. And then you have your jamb for the door. So that's giving you like 3.5 inches. So in normal cases, that would be fine. You would have plenty of room for casing. But maybe this client has chosen a casing that's like 6 inches wide. Well, now what are you going to do? When you go to put the casing, that's the nice trim. We'll talk about that coming up in another chapter that goes around the door. Well, the reason they put 6-inch casing is they like it. It looks nice. It's wide. And now you're going to cut it to put it up the sides. Looks awful, right? So a little thing like when you're framing, to be thinking about starting with the end in mind and working backwards. Well, the end in mind is I've got, the end in mind is I've got a casing. I've got a casing around the doorway, right? So the end in mind is I've got this casing. I want to make sure that I've got enough room between it and the wall so that it doesn't become ripped out or something like that. And you see that all the time with cabinets, kitchen cabinets. So you have a window here. When the cabinet comes, will there be enough space between the cabinet and the window for the casing, right? So you can really think those things out. Or did we get the cabinets that they're actually going to end up even on both sides so that it looks symmetrical? Or is one side going to be like this and one side going to be tight? These little things make a big difference. And to be honest, when you get into a rhythm with it, it doesn't really take much extra time. That's where I think I mentioned about the checklist manifesto and using a checklist to check things. Did I say that in the video? Sometimes I forget with different classes. So if you have a checklist of things that you go through to check the framing, then you're less likely to miss something, because it's very easy to miss something in that process. So good site supers will have a checklist so that they don't miss on some of these elementary things. And then you're doing the frame check at that stage. Then the next stage is going to be, well, you're going to have the shingles put on the roof. You're going to get the windows to enclose the house. And then you're going to be doing the rough-ins. You're going to have the building systems being roughed in, right? And the building systems can be roughed in while the brickwork is going on the outside. You can have both going on at the same time simultaneously. And when the rough-ins are done, you're going to do another inspection, and you're going to check that every outlet is where it should be, that every switch is where it should be. And the best builders, they do a walkthrough with the client, and they walk through so they can see where all the outlets are, and they explain everything. Because if a client at that point says, you know what, I would like an extra outlet over here, right, on this side of the wall, or I would like an extra outlet up on the wall in the middle so I can plug I'm going to put my TV on this side of the wall, right? So that's the time to do it, because it's very easy to do. It's not easy to do once the drywall is on, once it's painted, and once the trim and everything is done. Then to add that outlet, instead of it being like $100, it becomes like $1,000. So you don't want to get into those situations. So you give the clients opportunities. Now, the best is before you start construction, but to be honest, a client doesn't know what they really want until they actually start walking the space and that sort of thing. And you'll find in custom homes, it's a lot more communicative with the client than say production. But even production, like Mattamy Homes, they have specific times that they make sure that they do a walkthrough with the client, because they want to make sure that if there's any issues, it's easier to fix them at this point. So I think that's about what I wanted to cover. So just to reiterate, the test will be on week 9. So that's right after the intersession week or break week, if whatever you want to call it. It'll be on Monday at 9 o'clock. And I'll tell you how long you have for it, likely an hour and 40 minutes, something like that. There'll probably be around 35 to 40 questions in that zone. And there will probably be some questions from the Brook drawings. So make sure you have access that you can flip to the Brook drawings. The Brook drawings are, if you for some reason don't have it with the textbook, I have the Brook drawings loaded in the assignment tab of the assignment for this course. So they're digital. You can have it printed or digital, whatever, to look at it. And what I would be doing is preparing for your test, looking at chapters 5, 6, 7, 8, 9. And this next one, so 9A, B, C. And so there's the Brook drawings with that. And I'm going to release another video, which is called 10C, which is again on reading the Brook drawings for details and looking at details and understanding the detail side of things. So I would include that questions could come out of that 10C, but I'm not really going to pull questions from 10A or 10B too much for that, for the actual test. So hopefully that gives you a good idea, but what I'll do is when I get a better handle on the test, I'll do a short video so you can reference the video on what to look for the test. So I'll try to have that video up by, say, Friday night. Any other questions? Great. Okay, so I will see you Wednesday then, I guess, most of you anyways, unless you have an exemption. All right. Have a good one. See you for now. Well, there'll be a quiz this week too, by the way. You'll see it.
All right. Thanks, Tom. Have a good day. Bye.
Okay. See you, Max. Take it easy.
Yeah, see you Wednesday, Tom.
Okay. Take it easy, Sean.